So I'm going to talk about some things we've been doing, building on work of Gerald and Jonathan and various people, looking at how we can use the version of the process tensor that they've kind of developed and the numerical techniques they've developed to compute this processor, not to simulate the dynamics of some system, but to work out how to control some system in order to do what you want it to do. So this is the problem of optimal control. And generally, the goal here is to figure out how you can implement some quantum process. And I'm really thinking about processes here at the level of single gates by designing some control field. So we might think about, for example, state transfer processes where we're in one state, we know, and we want to transfer it to another state. A slightly more general version of that is a quantum operation, implement some rotation gate or something like that. It's only slightly more general because in that case, you don't necessarily know the state you want to start in. You'll start in some generic pure state. You can do this. It's not much more difficult to do than this. And then there's other kind of actually more interesting, perhaps things like doing qubit reset or qubit erasure, readout processes, and even transmitting information between different qubits, which is broadly speaking communications and sensing. So we're starting to look at optimizing these processes and determining how you can do them numerically using the process tensor. And we're particularly interested just to orient you in two particular systems. One is this kind of inorganic quantum dot that we've seen here. So as a simplified model of that, you can have a two-level system with a ground state, which is no exciton in this dot, and an excited state, which is one exciton in this dot. These are all open quantum systems. And in this case, this is an open quantum system because it's got this bath of phonons. And you can control the state of this thing using laser pulses shown here, which you can shape to manipulate the state of this in particular ways. And actually, the place I got into this kind of business was doing some work with experimentalists in Cambridge who implemented adiabatic state transfer in this semiconductor quantum dot, which is a nice way of deterministically preparing the excited state, which is a nice way of making a deterministic single photon source. The other thing we're kind of working on, and this is more in the context of reset, is things like these superconducting circuits, so things like transmon qubits. It's essentially the same sort of problem. Here you have baths, which are resistors and things in the circuit. You have various other baths. You have some nasty baths, which are 1/f noise, and you have baths which are to do with waveguides and the photons in the circuit as well. Again, you can drive these things, in this case, using microwave pulses. So typically what we want to do is some process, and we want to know what shape this control pulse is going to be. So I just want to start off, before I talk about optimal control, about some general issues of kind of what determines the performance of these things and how you might specify it. So that's a little bit perhaps related to our questions about how do we want to benchmark methods. What do you care about in terms of the performance of these? And then I'll talk about the notion of process tensors and how you can use them for optimal control. And there's a trick to making this efficient, which is a form of backpropagation algorithm that I will show you in diagrams. I'm afraid this is one of those things that's embarrassingly obvious after you draw the diagram. I would like to say that we just drew the diagram straight off and went ahead, but actually, of course, we waded through mountains of algebra and then thought, I'm going to draw the diagram, and realized how obvious it is. So I hope this is still worth drawing, even though it's obvious. I think there's some pleasure in that. And then I'm going to show you some results for some quantum state transfer. And I think these results give you a bit of a perspective on this performance issue, and in particular show you how you can use a non-Markovian environment to improve the performance of this process through really non-Markovian effects, which we don't fully understand, but I think I've got some kind of rough ideas of what's going on. Okay, so let me talk about performance, and let me do the very simplest problem, a two-level system. Here's a block sphere for a two-level system. Here's a Hamiltonian for a two-level system with two time-dependent driving fields or driving parameters. And I might say there's a state transfer problem. I've got some initial state, say it's the x minus state here, and I want to know how to get to a target state, say the X plus state. Or I might want to stay in the same state, and then this is a problem of preserving coherence, essentially. So the question is, how do you choose controls to reach this desired target state, and what are the kind of limitations on how you can do this? Well, let's do something really dumb. For a unitary process, it's fine. It's quite straightforward. This process is possible given two constraints. First of all, you need to have enough control parameters, and you have to have enough time. And that's kind of fairly obvious if you think that this driving field here, you're just rotating the block vector around the instant effective magnetic field with components delta and omega. So I can explore from here anywhere on the block sphere if I've got fields conjugate to two of the variables. So I can do any two rotations, I can make any third rotation. So that's why you need enough control parameters, and for a two-level system, 2 is enough. You also need enough time, which is kind of obvious from the point of view of the block rotation, right? I process, say, if I want to go from X minus to X plus, I just switch on a field along the Z, so this field here. That makes the block vector process around like this, and I stop after here. That's just a pi pulse. Yes, pi pulse. Okay, now clearly my Hamiltonian is going to be bounded. I can't apply infinitely large fields because that would have an infinitely large energy for this system. And so there's always some limit at which you can the rate at which you can process here, some maximum value of the field you can apply here. And that means that you need enough time to get from here to here in order to do this process. So if you think about that process and just compute a silly picture, say what is the infidelity at the end of the process from this, starting from this initial state to this final state, and you plot it as a function of the time you have to implement that process. If you have some bound on the field, you'll get a curve like this. If you have enough time, the infidelity is 0. You can do it perfectly. If you don't have enough time, you get some infidelity to the process. And all that's happening here is you're just kind of trying to go as far around the block sphere as you can, and you're not getting there. Now, these brings in a thing which is one of the things we started thinking about here originally, and I'm not sure how much we need to think about it in this talk, but this is connected to the idea of quantum speed limits. There's clearly a quantum speed limit here associated with this process, and it comes from this bound on the Hamiltonian, and it's basically this thing here. Now, there are various bounds people have derived over the years. There's a quantum speed limit here and one here. These are basically energy time uncertainty, and they say you can't in general do these processes faster than essentially the inverse. This is the standard deviation of the energy in the state, the expectation value of the standard deviation or the uncertainty energy. This is the inverse of the mean energy. If you take the lowest energy should be 0. Now, these quantum speed limits are sort of sometimes useful. They don't necessarily tell you how to do it or even that you can do it. And this particular problem I've set up because this is one case where you can see that you can do it and exactly how. And actually this simple problem, you can show that these bounds are actually saturated. So this is as fast as you can possibly go and you don't have to do it.
I have a question.
Yeah.
Are you predefining the functional form of the Hamiltonian?
No, I'm allowing it to be any continuous function of time.
So what are you actually?
Oh, so I mean,
the shape, the form of the Hamiltonian, or the parameters of the specific outputs?
In general, I'm saying that the form of the Hamiltonian looks like this, and these two functions, omega of t and delta of t, are arbitrary functions of time.
Yeah, so in a way you predefine the Hamiltonian, you're just optimizing the parameters, but sometimes you might not know what is the shape of the Hamiltonian, or the form of the Hamiltonian.
Sure, yeah, that's yeah, indeed. If you don't know the Hamiltonian, you can't, well, yeah, I don't know if you can do it.
Sufficiently flexible ansatz for that circuit is important.
Okay. Was that another question? No. Okay. Okay, so let's think about what happens if you go to the real world now of open quantum systems. The point is now this thing is not going to be perfect, right? It's an open system. There's going to be some information flow into the environment. There's going to be some decoherence, or the entropy of my quantum system is going to increase, or the purity is going to decrease, right, as this information flows into the environment. So there's now two things, right? There's not just speed, but there's how well did you do this, right? What was the fidelity or infidelity with which you did this operation? So you now end up with curves where these kind of plots of infidelity as a function of process time might look a bit non-trivial, right? There's not just one line you can draw here, because maybe you want to trade speed for performance, for higher fidelity. So this brings me to the story of the tortoise and the hare, which is the subtitle of this talk, right? The tortoise and the hare race, and the hare is absolutely sure he's going to win. And I guess you probably think the hare does win in a quantum system. Why might you think the hare wins? Well, you say information is flowing out of your qubit into the environment, and you're just losing information at some rate. Okay, so if you're just losing information at some rate, you better do the process as fast as you can, and that will also give you the highest fidelity. So if you took a simple Markovian picture of decoherence, so here's the perfect unitary case. If you took a simple Markovian model of decoherence and add it to this perfect unitary case, you'd get a curve something like this. Here you don't have enough time to implement the process. As you go to longer and longer times, though, you're starting to get more and more decoherence, the state's going away. And so actually, in that case, you want to work as fast as you can. So it seems like the hare is going to win and the tortoise and the hare story is not relevant. But hang on, this statement that information flows into the environment and doesn't come back is one of the notions of Markovianity. And we know there are non-Markovian baths. So if we have a non-Markovian bath, maybe it's possible that if we have enough time, we can recover some of the information that's lost to the environment during the subsequent evolution, and not get a curve which looks like this, where you want to work at the speed limit, but maybe you want to go slower because you can do better if you do. So that would be the tortoise, in fact, winning, as he does in the story. And what I want to show you is an explicit protocol we discovered using numerical optimal control that does this and shows you that actually the curve for a non-Markovian system can look not like this, but I should have put it at the beginning, but like this, right? Here's the result. It gets better the slower you go. So that brings me on to a very dangerous slide. We're interested here in the state, mostly. I mean, we may be interested in other things, and this formalism can generalize to other things that you can try and optimize, but let's focus on the state. In other words, the density matrix you get by tracing over the environment. One of the ways you can think about the difference between these systems is to say, well, do I have a flat spectrum for the environment, or is there some environmental structure? If I have a flat spectrum, that tends to mean I just get one-way information transfer. But if I have a structured spectrum, the environment can ring and the information can come back. And this kind of flat bath notion is often violated. So the case I'm going to talk about, this phonon spectral density for, say, a quantum dot, looks something like this. It's smooth. It's a superohmic spectral density with an exponential Gaussian cutoff. I think it's Gaussian actually in reality because it's the wave function of an oscillator. But it's definitely not white. It's not a flat bath. And this scale here is in inverse picoseconds. This is essentially also the time scale on which you want to do stuff to this thing, right? This is the time scale of an ultra-fast laser pulse. So there's no clear separation here between the time scales of the bath and the time scales on which you're trying to do the control. I had this slide for years, and when I saw some of our results and started to think about whether they really do need flat baths or structured baths or what's going on, I sort of put in a bit of a hedgy twiddle sign here. I'm not sure quite that this is the whole story. And actually, after some of the discussions we've had at this meeting, I think maybe I should just cross out this whole thing and say, these are interesting effects associated with non-Markovianity in structured environments. Okay, so let me come on and talk about the method for doing optimal control using these process tensors. So to start off, let me kind of just clarify or specify the particular kind of process tensor I'm using and give you the diagrammatics I'm going to use, because this is essential for the backpropagation algorithm. So I'm doing a diagrammatics which looks like this. This is, in the green box, is the process tensor. These are matrix product operators which are lurking inside the process tensor. This is a state, which is a density matrix, a reduced density matrix of a system, and I'm in Liouville space, so this is a single index object. And this is a process tensor which you can stick a state in here. It's got these slots, and out here you get a final state where, if you want, you can stick some operator to do to get an expectation value at the end. So I'm going to assume that the system and environment starts in a product state, and it evolves to some final time. And in that window of final time, there's some set of intermediate times, which are these slots where you can apply interventions. So you can do positive maps from an output state at the first time to the input to the next time. So that's I think, the original notion, perhaps one of the notions of the process tensor. So I'm going to use, so this is the notion that's a multilinear map from the set of quantum operations on the reduced density matrix at these time steps to the density matrix at the final time. Now, what these things actually are is they're things that Gerald and Jonathan and people wrote code to extract from the discretized path integral. So really, our process tensors have hundreds of time steps, which correspond to a small time step that you get when you discretize the path integral numerically. They definitely don't just have 4 time steps. And the point is that these things can be efficiently constructed in this matrix product operator form. Now, I think it's probably clear, but let me just remind you that because I don't know if you focused on this kind or mixed both kinds up, the specific process tensors I'm going to talk about differ a little bit from this, in that the thing you think of as the system Hamiltonian is the thing I'm going to stick here and take as the interventions. So I'm taking the system Hamiltonian out of the construction of this, which just describes the environment. So the things which are going to go in here just describe the propagation with this Liouville superoperator, which is just a commutator with the system Hamiltonian, and this is the system Hamiltonian. And that's that, and they just slot in here. Okay, so this is already a great idea for doing optimization, right? I mean, it's almost exactly the setup of optimization. Because if I can calculate this thing, then I'm saying I just slot in here the controls, the things I'm trying to optimize, and that tells me what I get out, and I want to make it work. So these are my controls, which correspond essentially to the Hamiltonian, and therefore at each time step. Okay, so let's do some more diagrams because they're cool. How do we apply this to, say, optimizing state transfer? Okay, so we'll have some initial state, say it's x minus, and we want to choose the controls to reach a desired target state. So we need to choose some objective function. And the obvious one there is the fidelity. We want to maximize the overlap, essentially, between the state which comes out here and this desired target state. Yeah.
So do you constrain your control? Because the optimal way to do it is wait till the penultimate time, throw away the state, and then prepare the state you care about.
The controls here are unitaries implemented by this Hamiltonian. And I'm going to put bounds on the values of these fields, so I can't implement arbitrarily fast unitaries either. So in the sense, yes, the control is, yes. That's not a control that my optimizer is going to find, because I'm going to parameterize these to only include a subset of operations.
Sorry, that's not easier.
Yeah, no worries. Okay, so this is really nice because this fidelity, this thing we're going to maximize, has a nice diagrammatic representation. I just stick the transpose of the target state on the top of this diagram. So this is a tensor network diagram. And remember, this is a scalar. It's got no free legs, and it's exactly this fidelity, at least in the case where you have a pure target state. Okay, so what we want to do is search through numerically all these possible, within some subset of these possible control operations to maximize the value of this scalar. And in our case, that means finding these continuous fields that maximize the value of this thing. Now, there's a well-known thing in optimization. Suppose we have these controls that are parameterized by, say, p parameters. We want to find a maximum or a minimum. If all you can compute is the function, that requires of order p squared evaluations of the function. Why? Because you're trying to approximate the Hessian, and there's p squared elements in the Hessian. However, p squared evaluations of function is the same thing as p evaluations of the function and the gradient, because there's p numbers in the gradient. So if you can get the gradient, you can efficiently, you do this problem much faster, essentially, because you don't need to calculate so many numbers. Of course, that only helps if you can calculate the gradient more efficiently than calculating the function f p times. Okay, now there's a trick to doing that, which is the thing I'm embarrassed to say we didn't spot immediately, which is to do a backpropagation algorithm. So here's the fidelity. It's a functional, or a function really, because I've got discrete time, of the numbers which live in these propagators. So this is the matrix U appearing in here, and here, and here. And this is a multilinear map from the numbers which live in here to the fidelity. By definition, it's a tensor network diagram. Okay, so if this is a multilinear map from these things to this scalar, the derivative with respect to, say, one of these is just the same diagram with this thing emitted. Okay, so that still looks like it takes lots of calculations, because you'd have to calculate this diagram and then this with A emitted and this with C emitted and so on. The backpropagation algorithm, though, gets you them all in two contractions of this tensor network. And it's kind of obvious with hindsight. So what you do, first of all, you do the contraction of these tensors in the way you would normally do. You start from the initial state, contracting the first matrix product operator for the first time step, contracting the first system propagator, contracting the next matrix product operator, and so on. And you build this network up from bottom to top, going forwards in time. The only thing you want to do now is just add one little step to that. You want to save the tensor you get at each of these time steps. So at each time step, you have a two-legged tensor, like this, that you want to save. That's forward propagation. You would have done it anyway. Then you do this from the top to the bottom, which is back propagation, again storing the time steps, the tensors you get at each time step. And then you can just stitch those together to get the whole gradient. So the first entry in the gradient vector, this thing with this, the network with this slot empty, you can take the forwards propagation plus one time step and the back propagation to n minus one time steps, and you just contract this pair of legs. And you can just then stitch all those together and you get all the gradient. So basically you need to do two constructions of the whole network and then n contractions of these internal legs. So this is well known for Hamiltonian dynamics and even Liouville dynamics. And it's quite interesting to see one of the differences, though, that if we have got, Markovian dynamics, if you've got a Markovian master equation, you wouldn't have these kind of internal legs here. You would just propagate kind of up and down according to a time local propagator. And then the thing you would need to store just has one leg, which is just the kind of result after each time step, and the result after each time step going backwards. So if you had a Markovian evolution, you just need to store the reduced density matrix after each time step going forwards and backwards, and you stitch those together. Here you've got to store these two-legged tensors, and really the point is it's this internal bond leg that's kind of letting the information flow backwards and forwards in this network and letting you do the optimization in a non-Markovian system. Okay, so how are we doing for time? We started pretty much on time, didn't we, John? Yeah. So let me show you the results, which I've already hinted at. Here, I'm going to do this optimization numerically as a function of the time of the process. And I'm going to have, oh, I've changed notation. Here's my Hamiltonian. I'm going to put some bounds on these control fields to stop it doing infinitely fast unphysical things. And recall that we had for unitary dynamics this kind of thing. It's either perfect or imperfect, and they're separated just by a single time step. It's actually interesting. Yeah.
Question about the algorithm. What's the speed on that? In the sense that can it be implemented in real time? If you were
Depends on, I mean, real time. How real time for? I mean.
So you had a cubic you control.
Yeah. Quite possibly, if you have a simpler. I mean, I can tell. So one optimization of this takes, 30 seconds on a laptop, and this has 500 control parameters. So you could certainly, it may be a bit too much to pull, but you could certainly think of simpler parameterizations and reduce the thing a bit. But yeah, I mean, it's not. For these problems, it's not much more difficult than just implementing the Markovian evolution in real time, which I think people do. And actually, the difference is just how many more contractions do you have to do in terms of this forward propagation. So it's just to do with what this bond dimension is. And for the problems we've got, I think the bond dimension's gets up to about 40 in the middle of the process tensor. So we're doing about 40 times more work than you would do to do the Markovian evolution. So yeah, it would be interesting. It would be great if you do it.
How do you tune the time step, right? Because you want it to be small, I reckon.
Yeah.
But large enough such that the network doesn't get very large.
Right. We just tune it based on the correlation function of the bath so that you capture the structure of that correctly. And actually, it doesn't necessarily need to be small compared with the timescales of the evolution of the Hamiltonian, because you can put the Hamiltonian propagator in exactly if you think that the bath doesn't kind of know about that fast dynamics. Yeah.
So I'm trying to understand here what this is intended for, I suppose, to state systems.
Well, not necessarily. I mean, it doesn't. These particular methods aren't designed to reduce the difficulty of simulating in terms of the size of the Hilbert space of the system. It's designed to let you simulate the bath system problem with a relatively simple system.
I understand, but
yeah.
In practice, I mean, if a system is huge,
Sure, but I mean, this thing is to a reasonable approximation. This transmon is to a reasonable approximation a 3-level system. I mean, to a half decent approximation, it's a 2-level system, and to a really damn good approximation, it's a 3-level system.
Okay. So my question is, so I suppose, and also from some experience with work we did a long time ago with these kinds of controlling systems.
Yeah.
If the system bath coupling is large, you're not going to be able to control very much. So this is all most used for weak coupling situations, or intermediate coupling maybe.
I think maybe we should talk about that. I don't know, and I don't think we will fully understand the implications of methods like this till we try them. Actually, I don't know the answer to that.
My question is, for these types of systems, say with a few states, 2, 3 states, a
Yeah.
few states, and coupling that is not huge, and like typical situations. Isn't this done in the simplest way using, say, old coffee? And
well, well,
simple.
okay. Well, we'll maybe come back to that. I don't know, and I'm not quite sure I know why what matters. I mean, there's some interesting things I think we found in terms of how to do it. Maybe we need those benchmarks. And actually, I will post these benchmarks. The figure I have, the key figure of this talk here, which shows the result of doing, I don't know, it's about all these different optimizations, each one over several hundred control parameters in a non-Markovian system, and that takes half an hour on my laptop. So I'm not sure that one can do that with other methods, but maybe that's a benchmark to stick in our benchmarks table. Anyway, so I want to show you some results of this because, it's physics, and I like some physics in my talks.
Can you put also
Yeah.
constraints in your optimization?
Sorry?
Can you impose hard or soft constraints?
Yeah, we do in this, and I mean that comes from the minimization algorithm used. So we just used an off-the-shelf BFGS minimizer, which allows.
That's sort of like the penalties to the cost function, or how do you impose?
No, that algorithm allows for hard constraints, but not soft constraints. So we just told it to put in hard constraints. I think
the question is,
yeah.
When you store these scores, in your experience, how does the rank evolve along, the middle of the tensor process? Because presumably you need information for all future times.
Yeah. I mean, that's really a question for Gerald, and it depends on the problem. I mean, I can plot it. I know what it does for this particular problem. And at the beginning of the evolution, of course, it's nothing because you've got no history to store, and it grows as you go up this way, and then it tails off again. And in the problem I'm showing, the peak bond dimension in the middle is about 40 or 50. So that's what I'm saying. It's about 40 or 50 times harder than doing a Markovian problem. That answered it.
Yes, yeah, that is exactly the same thing we see in the tensor traits.
Yeah. Okay, so before I show you the results of the optimization, let's just take that simple control process and just put it in this model. In this case, we have a coupling to SZ, and that simple control is just to drive along SZ. Sorry. Yes, drive along SZ, that should be SZ, not SX. So actually, this is an exactly solvable model. Or you can use tempo and plot the infidelity, and you find this result here. It's now not perfect infidelity. And actually, this is just the decoherence that comes from forming the polaron in the independent Moser model. You just displace the oscillators and it relaxes. And so actually it's interesting, this is not the Markovian result you'd expect, because this control in this model has no interesting Markovian dynamics. The only decoherence it has is to do with the quenching from the initial state.
Sorry, you have a dot here, right?
Yeah.
So what do you mean by unitary? What is unitary here?
Where did I say? Oh, so unitary. So this is a comparison. This is no bath. This is the control that you would have implemented in the unitary dynamics, but with the bath. Okay, just for comparison. Just if you, and actually the other reason to show this is what we take as the starting point for the optimization. It seemed like a good option. So now you can see what it does and plot the achieved optimized infidelity as a function of the process time. As you'd expect and hope, it's always better than the unoptimized case. Otherwise, we've done a really bad job. The interesting thing is that as you go past this kind of speed limit of the unitary dynamics, where you've kind of got enough time to stretch out the dynamics and do interesting things, you start to see a noticeable improvement in the fidelity as you go to longer and longer times. I don't know how far out that continues, but it's an interesting effect. So here, unlike the unitary case, where you have a simple speed limit, it's either perfect or imperfect, you've got speed and fidelity to think about. And unlike a Markovian case, speed and fidelity compete. So if you want higher fidelity, you can get it by going slower. So let me just show you a little bit of the optimized results. So here is, I think this is a 4 picosecond control. So we're sitting here. This is the Hamiltonian in the sense that this is the field conjugate to Z. And that's not changed at all from the initial guess. So you're just doing something around the Z axis. But what the optimization's done is it's put in this kind of kick along the X and then some wiggles and then a kick at the end. And that produces some dynamics on the block sphere, which you can see here. Instead of just going around the equator of the block sphere, it's kicked it down into one hemisphere and it's got lots of wiggling. Now, the interesting thing actually, I think, is if you think about the length of the block vector here, this is the length of the block vector in the unoptimized case, which is just the decoherence in the independent boson model. And basically what the optimizer's done is it's kind of stopped that, which I would interpret as saying it's managed to kind of prevent or recover the formation of the initial uncorrelated state from the polaron, right? It's kind of either stopping or rebuilding the product state that you started with at the end and removing the correlations you would otherwise build up with the environment. So you can look at a bit more, you can look at kind of, you know, if that's true, you would say this is a non-Markovian effect because it's kind of recovering the initial state. And maybe you can quantify that. So we've quantified that using one of these measures, which is based on information backflow. So this was Breuer, Lane, and Kilo, I think. So you say you take your density matrix, you start with 2.2 initial states in your system, and you calculate the evolution of those two states. And then you work out the trace distance between these states along that evolution, and you take the total amount by which it increases, right? So you pull out, you ignore all the decreases of trace distance, and you take out the net increase, and you take the maximum of that over all the pairs of trajectories on the initial state. So here is that non-Markovianity as a function of pulse duration. Of course, it's 0 at 0. This is the unoptimized case, and there is some. Again, it's not a Markovian dynamics. There is a bit of information backflow in the formation of a polaron. Here's the result for the optimized pulse, and when you get kind of out here, you start to see it kicks up again. And so you can say, really, it is pulling information back out of the environment, and what that must be doing is decorrelating, removing the correlations between the system and the environment that would have built up otherwise. So actually, this is a slightly more information about this. This is the kind of cumulative non-Markovianity as a function of time. And so here's the independent boson model, and you can see that there's some point about here in the dynamics where the states actually start to separate out for that maximal pair. For the optimized dynamics, those states separate out further, and then there's a bit more of a separation out at the end. So this measure is the net increase in the trace distance between states under the evolution, maximized over all pairs of initial states. This is take the pair which maximized that net increase and look at how the trace distance has increased over time. So this is a measure of how much information has come back from the environment to the system during the process as a function of the time of the process. I mean, it is just the information content that has flowed backwards from the system to the environment. Okay, so I think that's probably my time. So my conclusions are that process tensors can be used for the optimal control of open quantum systems with memory, so non-Markovian systems. And that's what I mean by general here, not general system Hamiltonians, but reasonably general models of open quantum systems. The interesting thing is that, at least for this simple case, slower processes can produce higher fidelity, contrary to Markovian processes where faster is generally going to be worse. Sorry, slower is generally going to be worse. So the tortoise does indeed win in this case. And the increased performance we can associate with an increased non-Markovianity under this particular measure of non-Markovianity. And I put an open question there, physical mechanisms, which I've been bending people's ears about what I think is going on, but maybe I'll leave that for another time. Thank you.
Question, Alex. Oh, really nice talk. For the back propagation, I was just wondering, is this a sort of particular instance of the sort of ideas that go into what's called automatic differentiation? Or
yes, automatic differentiation is back propagation applied to the tree of the differentiation process. Yeah. Yeah.
The tensor network theories.
So, you know, if you look at the sequence of operations when you do with back propagation and you wrote that as a sequential process, sorry, when you do differentiation, you can write differentiation as a sequential set of operations. Automatic differentiation is does that from the outside in, or yeah, normally you do differentiation from the inside out, right? And yeah, automatic differentiation is the reverse chain rule. And actually, so it's the general name for that class of methods are adjoint methods. And this is an adjoint method. But the nice thing about this is that it's really obvious in tensor network diagrams. So all of those, so you could do all those, yeah, you could express all those as, you know, you are basically saying if I can construct something forwards and construct it backwards, I can calculate gradients.
The question about, you know, time steps and, you know, that sort of thing. Would it make any sense to actually use some of the you know, like zygote in Julia?
Well, actually, we do use automatic differentiation because this algorithm gets you the gradient derivatives of the objective function with respect to the elements of the propagator. So you then have to relate those derivatives to the derivatives with respect to your control parameters, and you can do that using automatic differentiation.
Thank you.
I think we didn't, we just did it with finite difference to start with, but I'm sure in the final polished version of the code, it will use automatic differentiation.
So do you have, can you tell us how well one can do as a function of the system bath properties?
No, we haven't explored varying that particular parameter. I think it might depend on, I don't know. I think it might be interesting because I suspect that the improvement is more noticeable for stronger coupling, right? Because the effect of the formation of the polaron on, oh, do you mean about the optimization or do you mean about the calculation? Okay, yeah, the short answer is I don't know. I suspect it might be more dramatic, but it might only be more dramatic relative to a smaller, smaller thing, so.
What was the spectral density that in the example you showed?
It's a superohmic spectral density with this, so it's about 0.3 is the peak value of the spectral density in a problem where we're thinking about timescales of picoseconds.
Do you know the reorganization? Or something?
Not offhand, though. Yeah.
So maybe a comment on that first. So you can always do dynamic decoupling, but rate at which your pulse becomes faster and faster with the coupling, with the system coupling. Yeah, there's a function of coupling in a system environment. However, this is not dynamic decoupling, and it's quite nice because we have shown that there are regimes where dynamic decoupling breaks down.
But yeah, okay,
Right,
yeah,
but you can still do pretty good optimal control with process tensor,
Okay.
with optimization, but
yeah.
using maybe less sophisticated optimization methods.
Okay.
The question I have is, have you looked at whether this is related to methods developed by Silva and Lorenzo Viola, where they're
These kind of decoupling,
Yeah.
these dynamic, you mean dynamical decoupling type phenomena?
it's
Is it
similar,
slightly different?
but effectively they do they do a spectroscopy on the path and
Okay.
use that to control the.
It may be. That sounds so. I'd appreciate the reference. That sounds like it may be related. I think one difference though is that I'm pretty sure that whatever's going on here, you can't think of it in terms of a kind of mean field treatment where you're saying, I'm just driving the bath with the expectation values of the system. I think this is more subtle and is probably some kind of interference effect where the interference along the different pathways gets tuned to rephase the bath at the right time. So you can do something interesting actually, which Gerald suggested, and in the style of showing you how easy these calculations are computationally, I just did, which is you can take this optimized control and where's the block vector, and continue the evolution as if you switch off the Hamiltonian after that. And basically what you get is this translated onto the end of here. So you really have basically stopped it forming the polaron, and then it drops back. But it's not like dynamical decoupling in the sense that, or maybe a more sophisticated versions of that, in the sense that there's information backflow here, right? Dynamical decoupling things just stop the information going in the first place. There's definitely a role here for kind of recovering the information.
Can you maybe say a little bit more about those conditions where dynamical decoupling breaks down?
Yeah, so you require if you have too much time between two pulses, then it just doesn't work. Like even then, if you do an optimization on the process tensor, you can retain you can get infidelity of 0.01. Really good.
I mean, we actually slightly contrived this by putting the bounds on the fields in such a way that dynamical decoupling wasn't going to be achievable, right? That you can't. We told it we don't want you to find control fields that are fast compared with omega c. And actually, that's another thing that may be worth bearing in mind. Well, I think all of this physics, none of it's in the kind of scaling limit of the spectral density, right? This is all to do with the particular structure of the spectral density and where the peak is and things like that. It's not just, you know, is it ohmic or super ohmic or whatever. I think it's critical what it is.
Yes, two questions. So I would imagine that the quantum speed limit will change if it's for open system quantum dynamics, but your calculations doesn't really seem to suggest that. And also about the back propagation for the open system quantum dynamics, is it always, I mean, is it stable, or I mean, is it accurate enough? Or...
Okay, let me take those questions separately. So I talked about the quantum speed limit for unitary dynamics, and I didn't talk about the quantum speed limit for open dynamics, partly because I think the second one is much less useful for the point I was making, that in an open system, you need to consider speed and fidelity. It's not just a single number that you can quote. Now, there are quantum speed limits. So there's this one from Defner and Lutz, which says that the time to evolve between two states must be like this. This is the Bose angle between the initial and the final state. And this is basically, it's the time average of the magnitude of the operator which steps the density matrix one forward. So this is just a kind of generalization of the kind of natural closed speed limits. And I mean, all you do to make a speed limit is you take this thing and you stick some maximum norm type thing in that element.
Much tighter versions than that.
Right. I mean, this one, so we plot, so this one, of course, I mean, the other disadvantage is it doesn't tell you. So we plotted this for our process, and here's what it is for the optimized process. If you were actually saturating this bound, it would be this horizontal line, and you're quite a long way off. So I'm glad there are more tighter versions, because certainly when, you know, we're not saturating it. And I think you would certainly expect to saturate it out here if it's a proper tight bound, because here it's really just the unitary dynamics.
So if I understood correctly, the control parameters are the values of those functions fi at the pathing time steps.
Yeah, the values of the fields in the Hamiltonian at each time step.
How do you specify the functions in between those points?
There. We propagate across each time step using the exact, so the approximation is basically the controls are piecewise continuous across a time step. Sorry, piecewise constant across a time step.
Yeah, so for second question.
Oh, sorry, yes, you had two questions. Remind me of the second question.
So about the stability of the backflow for open system and the back propagation.
It works, and it works well enough that the well-tested numerical minimizers in SciPy don't complain about the inaccuracy of the gradients. So if the gradients were, if there were stability issues, I think, you know, minimization using the gradient wouldn't work. Right.
Did you have to do it a bunch of times, or like did it get trapped, or did it always survive?
We found we haven't really explored actually the kind of issue of the structure of the space, because it's obviously really super complicated. We found fairly, I mean, actually, let me show you something. So one thing we've noticed is that these solutions that we have looked at are sort of broadly consistent structures. Now we're starting from a similar the same kind of class of initial state. But there's obviously not lots of other solutions near the thing that we're looking at, because we find broadly. But if we start from a very different initial condition, we can find different things, certainly out here where you've got lots of time. And that you should probably expect that, right? I mean, if you give it too much time, it can do what it likes on the block sphere, and it's just got to get from here to here. So actually, let me just show you. There's a nice sequence of pictures here. These are the maybe look at this. This is the block sphere, optimized block sphere dynamics, and this is for the case where I have a really short process duration. So if I step forwards through these, I'm going to be, if you look at this, this is what happens for longer and longer pulses. So you see it can get further and further round, and then it kind of goes down. And the dynamics kind of out here is broadly consistent. Actually, if you go right out here, you start to get really big wiggles, which maybe it's starting to decide it could do some dynamical decoupling as well as the thing, if you've got enough, and if it can ram into the bounds.
Last question, Matt.
Very nice, Paul. Maybe a comment more than a question. Does the hair deserve a leg up? Kind of thinking about the specific problem you have, and if you sort of think, but you've also got a finite T1 time of maybe half a nanosecond or something. So you're probably just on the boundary where doing it even slower might incur penalty. That's not in your model.
This is, yeah, well, but I'm actually thinking here about processes. I mean, you know, any process like this, if you're going to do a sequence of operations, your operation is going to have to be far shorter than the T1. So, you know, so we're thinking about, that's the reason I was thinking about processes over about 5 picoseconds, was because of the, you know, few hundred nanoseconds, the thing's gone. So, I mean, that's the case with well, maybe not with the, well, yeah, with all of these systems, actually.